Yes. So let us start this session. In this particular session, we are going to start with something known as combinational circuits, right? So let us try to understand what are these combinational circuits and what are the different kind of combinational circuits which we are going to have, right? So before that, anyone knows C programming over here? Anyone knows C programming over here? Can I know in the chat box? Anyone knows C programming over here? Okay. If anyone knows C programming, can anyone write down a simple code for adding two numbers in C programming? Just a simple question. Can anyone write down, if you know C programming, can you write down a simple code for adding two numbers in C programming? Quick in the chat box. I know you're feeling that he's trying to discuss combinational circuits and he's asking to write down C programming for adding two numbers. Yes, that is a question. So can you write down a C code for adding two numbers or two variables? Simple question. It's not a very difficult kind of question. Okay, let's see who can write it down. Yeah, into sum a comma b, sum is equal to a plus b. And you're going to write down something known as hash include, hash include stdio dot h and something. I don't remember C language exactly. I think we are going to write down int main and in the sum is equal to a plus b, something like this, right? Yeah. So basically, over here, a and b are of how many bit width? We are discussing digital design only. We are not discussing C language. I wanted to explain related, something related to application level. So that's the reason I'm asking this. So here, a and b are of 32-bit width, and sum is of also 32-bit, right? So sum a and b are basically of 32-bit width. Am I right? Now, so you are developing a C language. You are basically developing a C file, right? So you are writing down a .c file where you are just simply writing down sum is equal to a plus b. Now, this particular application will be compiled and this will be converted into assembly language, assembly level language. Let's say suppose if you are working with x86 or or RISC-V or some kind of thing, depending upon what kind of architecture you are going to work with, it will be converted into that particular instruction set architecture. Depending upon what kind of instruction set architecture you are working with, it will be converted into those particular instructions, and from that particular instruction it will be converted into a binary format, and your processor is going to understand this particular binary format, and that particular processor is going to execute whatever the instructions was there. For example, in your machine language, in your assembly level language, it is going to look like this: add r1, r2, comma r3. Some kind of this kind of assembly language, assembly level language code will be visible, and that will be converted into binary format, and that particular binary format will be executed by your processor, right? Now, typically in your processor, you're going to have something like register file unit. You're going to have something known as register file, and you're going to have ALU and instruction fetch, right? Now, this ALU is responsible for adding any numbers or subtracting two numbers, or multiplying or performing division, or performing any kind of logical shift operation or logical operations, right? So what we want a plus b to be performed. So arithmetic logic unit inside your processor is going to perform this particular addition operation, right? Now, in your arithmetic logic unit, what do you think? What kind of circuit that will be present that is going to perform this 32-bit addition? Anyone wants to answer? If I want to perform this kind of addition operation inside your arithmetic logic unit, So see, so we have developed an application. That application is simply asking you add two numbers that will be converted into assembly level language by the compiler, and that is further, further it is going to convert it into binary language by the assembler, and then it is going to be implemented on your processor. Then processor is going to decide where to implement it. So we are going to have an arithmetic logic unit, and arithmetic logic unit is going to add these two numbers. Now, how the addition is going to be performed in the digital level? In the digital design, in the digital level, what kind of circuit is going to perform this addition? Is the question. Simple question. Okay, half adder, full adder. So I think many of you have heard about this kind of circuits like half adder, full adder, and ripple carry adder, and carry save adder, carry look ahead adder. Okay, so these kind of digital architectures we are going to design as an RTL design engineer. We are going to basically design. We are going to basically decide how this addition process is going to happen, how this arithmetic logic unit is going to perform my addition. Okay, so you might think we can simply write down in Verilog like a plus b. Okay, it might work with one bit, but if you're working with more than one bit, like 32-bit or 64-bit, this kind of simple a plus b is not going, it is going to work, but it is going to take enormous amount of delay. Okay, so you need to come up with special kind of circuits. Okay, what I mean, so I will explain you in a little while. Now, first of all, let us look into what kind of circuits which we are going to use basically for performing addition. Okay, so we are going to have the first basic circuit which is known as half adder. Okay, so this half adder, first let me draw the block diagram of this half adder. So half adder, it is going to have two inputs, A and B, and it is going to have sum and Cout, right? Can anyone tell me what is the number of bits this A and B is of? A is of how many bits and B is of how many bits, and sum is of how many bits and Cout is how many bits. For a simple half adder, what is the number of bits A and what is the number of bits B is of, and what is the number of bits sum is of, and what is the number of bits Cout is of? Simple question. Exactly. It is of only one bit. If you provide one bit only, it can only add one bit. So A is of only one bit and B is of only one bit, and sum is of only one bit, and carry out is of only one bit. That means you can add 0, 0, or you can add 0, 1, 1, 0, 1, 1. That's it. Either you can add only single bit numbers using a half adder, simple half adder. Okay. So how it is going to look like A, B, sum, and C. So 0, 0, 0, 1, 1, 0, 1, 1. So what we are going to have, sum is basically here it will be equal to 0, Cout will be equal to 0, and here it will be 1, 0, 1, 0, and 0, 1. This is my truth table of this particular, whatever the circuit, the half adder circuit. Now my question is, can I use the simple half adder circuit for implementing this ALU operation, A plus B, where A is of 32 bits and B is of 32 bits and sum is of 32 bits? Can I use this simple half adder for implementing this A plus B operation in my ALU? Yes or no? Okay. I'm repeating my question again. Can I use a single half adder for implementing? Can I use a single half adder for implementing this operation in my ALU for adding A and B numbers, which is of 32 bits, A is of 32 bits, and B is of 32 bits. We cannot use a single half adder, right? Obviously, we cannot use a single half adder because a single half adder is basically adding two single bit. Okay. Now, why are we learning? Because this is the basic foundation. Using this, we are going to do some combination, and we are going to combine few particular half adders, and we are going to come up with an architecture. So if you don't know about a half adder, then you cannot learn about the other architectures which we are going to learn in further sessions, right? Now, first of all, using this particular truth table, can anyone come up with the Boolean expression for sum and Boolean expression for cout using this particular truth table? What is a Boolean expression for sum and what is a Boolean expression for cout? Is a question. Exactly. How you are going to get these equations? So basically, the min terms for my sum are 1 comma 2, which is a complement b plus ab complement, which is nothing but ax or with b. And cout is equal to only there is one min term, which is 3, which is nothing but a dot b. Now, if you want to represent this particular circuit, so this is how it is going to look like. So you're going to have a XOR gate, AB, and you're going to get A XOR with B, and you're going to have A dot B for a simple half adder. This is what your half adder logic diagram is going to look like, right? Now, it's only used for adding single numbers. And if you are going to get, okay, let's say it is use it for only adding single numbers. Okay, fine. So let's say suppose if I want to add 0, 0, 1, 0, 1, 0, 1, 1. How many half adders do I need for adding this 4-bit numbers? This is A and this is B. Only single half adder is not enough. Let's say I'm going to have 4-bit numbers. Then how many half adders do I need for this particular addition? So my question is, a half adder can add only single bit numbers. Then if for adding my 4-bit numbers, how many half adders do I need? Is the question. Are you sure? For adding 4-bit numbers, how many half adders do I need? Is the question. Okay. Okay. So if you add this, how to add these numbers? So 0 plus 1 is 1, sum is 1, and carry is 0. 0, 1, 1, 0, sum is 0, carry is 1. And sum is 1 and carry is 0. And sum is 1 and cout is 0. Now, can anyone perform this addition using only half adders? Only four full adders, only four half adders you're saying, right? So how to add or how to implement this particular addition using only four half adders? Can anyone tell me? Exactly. Here full adders are required. I cannot use simply half adders for implementing this particular process. Okay. Because if you observe, half adder is only having two inputs, right? A and B. But in this addition, I need three inputs. Can you see this? So I cannot use a simple half adder for implementing this particular addition. Okay. So that's the reason we are going to another kind of circuit, which is a full adder, which has another input, the third input, which is nothing but C. Okay, so this is my full adder, and I'm going to have A, B, and C, the third input uh, for having the input as carry. So which was given by the previous stage. You can see this was being given by the previous stage. This is nothing but my C, and this is given by the second stage, and this is nothing but my C. Okay. Now this is my full adder. Okay. So how full adder is going to work? It is also going to work as a half adder, but it is going to take three inputs and it is going to provide sum and cout. So I'm going to have A, B, C, and sum and cout. So for three combinations, for 3 bits, I'm going to have total 8 number of combinations like this: 001, 010, 100, 101, 11, 101, 110, and 111. Okay. So this is how. Okay, 100, 101, 110, and 111. So this is how my full adder, and this is 00, this is 10, this is 10, this is 01, and this is 10, and this is 01, and this is 01, and this is 1. Okay, this is my truth table of my full adder. Can anyone tell me what is the expression for sum and what is the expression for carry is the question. What is the Boolean expression for sum and what is the Boolean expression for carry is the question. You can take your time and let me know what is the Boolean expression for sum and what is the Boolean expression for carry. AX or BX or C and carry is equal to, okay. So sum you are going to get sigma m. What is the sum? 1, 2 and 1, 2, 4, 7. So 1, 2, 4, 7 are your minterms and carry is basically 0, 1, 2, 3, 5, 6, 7. 3, 5, 6, 7 are the minterms of your carry. Exactly. So if you take your key map and if you can solve it, you are going to get AX or BX or CN, and this is AB plus BC plus AC. Okay. This is the equation you're going to get if you are going to minimize it, right? Now, let me first of all write down this carry again. So carry, I'm going to get it as sigma m 3567. 3567. Let me write down the midterms. So it is nothing but A bar BC plus B bar C plus ABC bar plus ABC. Now, instead of this expression, can I get any other expression? So instead of AB plus BC plus AC, can I get any expression from this particular equation? Anyone wants to solve it and let me know? You can take your time and solve this and let me know what is the expression you're going to get. Okay, let me solve it for you. So if you take C common in these two terms, one second, let me reshare my screen. Hmm. So if I take C common in the first two terms, what I'm going to get is C into AX or with B. Plus here if I take AB common, I'm going to get AB into C plus C bar, which is basically equal to 1. So the equation I'm going to get is AB plus C into AX or with B. C in into AX or with B. This is nothing but my carry, carry out. Okay. So this equation we are going to use and where we are going to use, let us discuss. Okay. Now, so this is nothing but my full adder equation which I'm going to get. So full adder, can I implement it using half adder? So full adder is not a circuit. Yeah, AB plus C into AX or with B. So full adder, basically we can implement using half adder. So let us try to understand how to implement it. So if you carefully observe over here, so what is this AB? So AB is nothing but uh, half adder carry. So using this, we can implement or we can get something. So if I want to implement a simple full adder using half adder, I can take two half adders. This is half adder 1 and this is half adder 2, right? And this is nothing but my A and this is nothing but my B. Okay. And I have C. Now what I'm going to do, I'm going to just give the sum to this particular half adder so that what I'm going to get over here and the scene is connected to this half adder. So that what I'm going to get over here, here I have AX or B and here I have scene which is nothing but AX or BX or with C. This is what I'm going to get in the case of my sum underscore out, right? Now, how to get my carry? So this is my carry and if you carefully observe the equation of your full adder, which is AB plus C into AX or B is your carry. Now, here, what is this carry? Can anyone tell me what is the carry of your half adder 2? What is the carry of your half adder? So if you solve it, carry is nothing but A dot B, where A is equal to AX or B into B is nothing but C. This is what our carry is. So carry of the second half adder is AX or B into Cin, and carry of first half adder is AB. So you can see AB is nothing but first half adder carry, and Cin into AX or B is nothing but second half adder carry. Okay. So this is nothing but my half adder to carry. So I can just simply perform the OR operation between these two. So what I'm going to do is I'm going to take this, and I'm going to perform OR operation so that I'm going to get my carry out. So this is how I'm going to implement a full adder using half adder. Is it clear for everyone up to here? Any doubts or any queries over here? Shall we move forward? Hello. Please respond in the chat box. Okay. Now, so okay, the problem which we were having that we need other kind of adder apart from half adder for adding whatever the scene was given or the carry which was given with the previous stage, right? Now, if I want to implement this 4-bit addition, obviously I'm not going to use a simple half adder, I'm going to use a full adder. Okay. So let's say if I'm going to have A is equal to 0, 1, 1, 0, and B is equal to 1, 0, 1, 1. Then how to perform the addition? I'm going to add first these 2 bits, that is sum is equal to 1. Let's say this is A0 and this is B0. I'm going to get S0. So for adding this 2, and let's assume that initial carry Cin is equal to 0, I'm going to have one full adder FA1, and whatever the carry which I'm going to get, which is equal to 1 over here. Okay. And for adding this 3 bits, I'm going to have one more full adder, which is FA2. And I'm going to get 1 plus 1, 0. 1 plus 1 plus 1. Sum is equal to 1, which is S1 is equal to 1, and carry is equal to 1. This is C2, which is equal to 1. For adding this 3, I should have one more full adder. For adding whatever the I'm going to get sum is equal to 0 and carry is equal to 1. For adding this 3, which I'm going to have one more full adder. So I need 1, 2, 3, 4 full adders like this. So I'm going to have one full adder, second full adder, third full adder, and fourth full adder. So this is FA1, and this is FA2, and this is FA3, and this is FA4, right? So I'm going to give this is A0 LSB, and this is B0 LSB, A1 and B1, and I'm going to give A2 and B2, A3 and B3. So from here, I'm going to get my S0 and C1. The carry is given to the second stage. You can see the carry which was generated, which was given to the second stage. And here I'm going to get S1, and the carry here it is going to given to here S2 and C2 and S3 and C3, right? So this is how my circuit is going to look like. For adding how many bits? For adding only 4 bits. Okay. For adding 4 bits, this is how my circuit is going to look like. Okay. Now, this particular circuit is known as a ripple carry adder because the carry is being rippling from one stage to another stage. It is also known as ripple carry adder. Okay. Now, here the main question is, let's say if I want to add 32-bit numbers, how many adders do I need for adding 32-bit numbers? Can anyone say me? If I'm going to use a ripple carry adder architecture for implementing a 32-bit number, then how many adders do I need? If I want to add a 32-bit number, then how many adders do I need for implementing it? Is a question. For 4-bit, I'm going to take 4 adders. Then obviously for 32-bit, I'm going to take 32 adders. Am I right or wrong? Yes or no? Now, okay. Now, what is the problem over here is if I'm going to consider this particular ripple carry adder, let's say, first of all, let's say if I'm going to take a simple XOR gate. Okay, because in half adder I'm going to use this XOR gate, and then in the full adder also we are going to use this XOR gate. Now, let's say this is nothing but my A, and this is nothing but my B, and this is nothing but my sum. Okay. Now, let's say if we are going to apply your A and B at time t is equal to 0. Okay. So you are going to apply your A and B inputs at time t is equal to 0. Let's say 1 and 0, you are going to apply at time t is equal to 0. Now, when you are going to get your sum, that is AX or B, which is nothing but 1x or 0 is 1. At which time you are going to get your sum? Am I going to get my sum at t is equal to 0? If I'm going to add these two numbers, if I'm going to apply A and B at time t is equal to 0, am I going to get my sum exactly at t is equal to 0? Yes or no? At the same time, am I going to get my output? Hello, am I audible? If I'm going to apply my inputs at time t is equal to 0, then am I going to get my output at exactly the same time? Yeah, obviously we are going to have some kind of delay, right? Because ultimately, this whatever the logic gates we are going to discuss or whatever we are going to have it in our digital design will be implemented in your CMOS level, right? So using CMOS only you're going to implement it. And whatever the inputs you're going to apply, obviously going to take some delay, right? So it is not going to get at time t is equal to 0, but it is going to take some time. And that particular time, which is nothing but my propagation delay. Okay. So the amount of time a logic gate is going to take uh, to provide a particular output for a corresponding input is nothing but my propagation delay. So let's say if this particular gate is having a propagation delay of 2 nanoseconds. Okay. Then if you're applying your input at t is equal to 0, then you're going to get your output at t is equal to 2 nanoseconds. Okay. Now the same concept apply to this particular 4-bit triple carry adder. And in our next session, tell me at after how many time units you are going to get your sum S3, and after how many time units you are going to get sum C3. Let's say in this full adder, we are going to have XOR gate propagation delays. Let's say, okay, XOR gate propagation delays 2 nanosecond, AND gate propagation delays 1 nanosecond, and OR gate propagation delays 1 nanosecond. Okay. So these are your time parameters which I'm going to give, and using these parameters, try to find it out after how many time units you are going to get S3 and after how many time units you are going to get C3, so that we will try to understand what is happening in the case of your 32-bit adder, or what is happening if you're going to have for a 64-bit adder. Why are we not preferring this simple kind of ripple carrier design for implementing addition between a higher numbers? Okay. If anyone knows, just try to find it out after how many time units you're going to get S3 and how many time units you're going to get C3. Okay. So we are going to discuss after why are we not preferring this kind of designs and all. Okay. Yes. So take this as a small assignment and try to find it out so that we will discuss the other kind of architectures we can come up for implementing higher number of bits. Like if we have 32-bit number, what kind of circuit I'm going to use? Okay, that we are going to discuss. Okay, and before that, we are going to discuss what is a combinational circuit. Okay. Yes. So that is what this today's session. Yeah. So if you have any doubt or any other query, you can stay and discuss with me.